All right, here is a video about lesson 9.5, factoring a difference of perfect squares. Okay, so first we did a little warm up here. I have two binomials, so I'm going to use the FOIL method and multiply. X times x gives me x squared. X times -4, -4x. 4 times x, positive 4x. And 4 times -4 gives me -16. Remember, there's always like terms in the center. When I combine those like terms in this case, they cancel each other out. And I'm just left with x squared minus 16. The result is a difference of perfect squares. I did show you guys a shortcut. I don't know if you remember. If you notice you have exactly the same terms in your binomials, but your signs are opposite, you just simply square the first term, 25m squared, and square the last term, which is 1, and then it's always subtraction between the two. That is a difference of perfect squares. All right, and the last one, if I would FOIL this out, I would have 4a squared minus 9b squared, resulting in the difference of perfect squares. First, you have to actually, it has to be a difference of squares. Remember, difference is subtraction. So if you see that you have a difference of perfect squares, you're going to follow the rule where you just take the square root of the first term, put it in the first place in both of your binomials, and the square root of the second term goes in the second place, okay? And their signs are always opposite. One positive, one negative, just like the ones on the previous screen. We can always check our work by distributing and make sure that we get back to that original polynomial. All right, so we did a couple examples here. So this is a difference of perfect squares. If it is not a difference of perfect squares and you cannot factor it, you just write the word prime. So I see here a squared and 4. Well, they're both perfect squares. So I set up my sets of parentheses. Square root of the first term goes in the first place, so that's a and a. And the square root of the second term goes in the second place, 2 and 2. And then our signs are opposite, 1 plus, 1 minus, and I'm done. If I look at number 2, I have n squared minus 64. Well, that's going to be n and 8 and n and 8 and plus and minus. 3 is a little different because the 81 comes first. Now, someone asked if they could rewrite it, but then you just have to make sure the negative, like, just don't rewrite it. Just leave it this way. When you factor it and you take the square root of 81, that's 9. That's going to go here and there. And then the square root of x squared, or just basically dividing it by 2, right? I just have x and x. And my signs are opposite, 1 positive, 1 negative. All right, for number 4, c squared minus 100. Easy peasy, they're both perfect squares, so c minus 10 and c plus 10. Look at number 25. Number 5, k squared plus 5. Well, that's not a difference. I can't do what I've been doing. All of these were subtraction. This is not subtraction, so this is a case of prime. Oh, if I could spell, okay? I can't factor that. That's done. Number 6 is a little like number 3, only now I have the variable with the number. So when I do the square root, when I factor the difference of these perfect squares, square root of 1 is 1. The square root of 49y squared is 7y. And again, plus, minus, donezo. All right, we'll do 2 more examples and then we'll go on to some other things here. So if I look at number 7, 9b squared and minus 100, both 9 and 100 are perfect squares. So I'm like, all right, I'm good to go. Boop, boop, boop. So 3b minus 10, 3b plus 10. Done. Actually, we'll do number 10. I'm going to skip number 8 right now. Let's do number 10. It says x squared minus 81y squared. You're like, what the heck? Well, you're simply just take the square root of x squared, which is x. The square root of 81y squared is 9y. Plus, minus. And that is it. That's in factor form. That is perfection. All right, let's look and see what I have on the next page. Oh yeah, I want to look at this one too. Look at number 13. That's totally crazy, but not really. They're both raised to the second power. They're both squares. One is a perfect square. So you set up your sets of parentheses. The square root of x squared y squared is just xy. And the square root of 1 is 1. and then plus, and then minus, and we done. Okay, hopefully it's pretty simple. I think everyone was not minding this lesson at all. Now, what happens when you look at your difference? You're like, okay, 2 and 72 are not perfect squares. If I take the square root of them, I get some crazy decimal, so that's not good. That means there's probably a GCF, greatest common factor. You have to divide by the greatest common factor, and the resulting polynomial should be a difference of perfect squares. All right, so if I look here, well, the GCF here is 2. So if I divide by 2, do not forget to put 2 in your final answer. I have n squared minus 36. And now I'm like, okay, 36 is a perfect square. Keep a 2 out front, and then you set up your 2 sets of parentheses. And minus 6, because the square root of 36 is 6, and n plus 6. I didn't give myself a lot of room, and I'm using my finger to annotate, so please forgive my handwriting. It's atrocious. Okay, 18x squared minus 50. Well, it's a difference with the two terms, but none of them are perfect squares, so now I'm like, oh, you know what? It probably has a GCF. So in this case, the GCF again is 2. So I have 2 times 9x squared minus 25. All right, now I'm like, all right, we're in business now because 9 and 25 are both perfect squares. I can take the square root of those. It gives me 3x minus 5 and 3x plus 5. Fantastic. All right, 32 and 18. Again, it's going to be 2. It's boring. I'm done with the 2. Let's look at 24. 45 and 20, and notice 45q to the third, 20q. So now my GCF includes a variable, so be on the lookout for that, because I need this to be to the second power. So the GCF for 45 and 20 is 5, right? And they also have a q in common, so 5q. So 5q is my GCF. Make sure you write that out front. And then we put in parentheses what we have left over. 9q squared minus 4. 9 and 4 are both perfect squares. Now I have my q to the second power, and I'm like, all right, I can continue factoring. 5q, parentheses, 3q minus 2, and 3q plus 2. Because the square root of 9q squared is 3q, and the square root of 4 is 2. Okay, let's try to see here if we can find another one that's a little crazy. Let's look at number 27. Oh, hold on a second, please, I'm sorry. All right, let's look at number 27. We have 80n to the fourth, 125n to the second. Well, let's see, what is gonna be the GCF with that? So you're like, all right, well, like, what if we try 5? All right, because I look at, whenever I see a 5 and a 0, I'm like, all right, I'm thinking 5. What else do they have in common? They have an n squared in common. So now my GCF is 5n squared. So if I write that out front, 5n squared, 80n to the fourth divided by 5n squared gives me 16n squared. And then 125 divided by 5 is 25n. I mean, no n. The n's cancel out, right? N squared over n squared just cancels out. Then I further factor it to 5n squared with my 2 sets of parentheses. The square root of 16n squared is 4n. The square root of 25 is 5. 4n and 5. Then we have plus and minus. Donezo. All right, that's all you need to do. Don't worry about the rest of the examples. They'll be fine unless you want more help. Just reach out and let me know. And you also have to complete the IXL BB4 to 85%. And don't forget about BB2. That is also due tomorrow. Have a great day. Bye.